So basically, so far, this lecture series has been a story of mathematical structures. And we started with the most basic mathematical structures, which are sets. Sets, yeah, being like, yeah, like I said, it's a collection of elements, except he doesn't define it that way. And between sets, we can define like an isomorphism between sets, which is like how we tell if two sets are set theoretically identical. And the isomorphism for set theory is a bijection. So it's just any map that can one-to-one map the elements of one set to another set. Yeah, and then but then building off of sets, we have the next layer of structure, which is topological spaces. And so yeah, so I guess, yeah, okay, I'll just, yeah, so topological space will be a set like M equipped with some structure O, which is like this, which like informally would be like the set of open sets that are subsets of M. And we would define two topology. We can also define, oh, whoops, not like that, two topologies to be set, like can be topologically isomorphic given the condition that is there exists. What was it? It was like, oh, okay, wait, I forgot this. But anyway, there's some, it's like, so the thing has to be oh my god, that was so long ago. I was flushing.
Yeah.
Okay. Yeah, so two things are set theoretically
Or topologically.
yeah, topologically okay, wait, actually yes, so like there's a, so for sets, for example, there's like, for example, there's a set actually like there's a, I don't know, there's a set P and a set Q, and then like if the bijection between them would be like a map phi, so this will be called the isomorphism, right? Or then the two sets are isomorphic. And the definition, how it always goes, is two sets are isomorphic if there's an isomorphism between them. So the homeomorphism between topologies would be is a okay, literally what I wrote is it's just a bijection that are continuous, and its inverse is also continuous, and it preserves the relationship between open sets of M and M. So, oh yeah, wait, no, that's literally how it's defined. It's continuous, right? Like, so
Yeah, just continuous. Yeah,
if we
exactly.
have the M, yeah, exactly. So we have the M and M from before, like the phi that is homeomorphic, and like homeomorphic just means it's continuous. And the reason why this preserves the structure of the topology is that continuity is defined with our open sets, right? So if it's continuous, it preserves the open sets, because the open sets define like the idea of two points in the set being next to each other. And okay, yes, so that was okay, so then after topological manifolds, topological spaces, we have topological manifolds, and they are basically just a special type of a space where it can be where there exists a continuous map from like M to like some some like d-dimensional R. Well, like actually no, it's there exists for every open set inside every open set of the manifold, there's this continuous map. And yeah,
so if that continuous map exists, then it's
yeah,
a manifold.
then it's a manifold. And given the definition of a manifold, given the definition of the manifold, all these the maps are continuous. So like, okay, so like the intuition for the manifold is just like, for example, like a torus, like for every like slice of the torus, open slice, you can map it to like, it's like it's like it's
like a Cartesian,
yeah,
like
exactly.
a section, like a portion of the Cartesian plane, I guess.
Yeah, exactly. So like it's how people say the Earth is flat locally, because locally it looks like 2D, right? So that's
Yeah.
why spheres are 2D dimensional manifolds. And because of this, because like now since we have this property of the locally being 2D, we can map our Earth into a like, yeah, we can map it into what are they called? Well, maps. So like we can create maps of the Earth that are 2-dimensional. So we can like represent the entire Earth manifold, the entire 2-dimensional manifold, in a series of like just like maps that are inside R2.
And when you say maps, you mean like the mathematical maps, or like the kinds of maps that we, like the sheets of paper that we use in real life?
I mean, oh yeah, for these maps, they're the sheets of paper that we use in real life. But also they are, wait. So it's like for like, for example, we have the Earth, right? And then we have like any location here. There is this some map, let's say
X.
Yeah, X, that goes
Yeah.
to the some portion of R2, and we call this, let's say, U, and then this combination of U, which is in R2, and the map X. So actually, oh yeah, we shouldn't call this a map. We should call this a chart.
Exactly. Wait, hold on. Do we call this U or do we call this U?
We call this U, right?
Right. So then what do we call this then?
We call this the chart. No, we just call this like X after U. No, I don't know.
Yeah, X of U. Yeah,
X of U, not after.
Right. Yeah, after implies it's like U itself is a map, but U is just
yeah.
the chart domain.
Yeah, okay.
I just gave away that word.
Cool. So this is and then if so we have this U of X, and then we can map a different part. Let's say we call this V, and then we can map this into a different section of R2. And then we can say this is a Y map, and then we have so then we have another chart, V, Y, and then if we take a collection of these charts and we have it so that the intersecting domain of all of these charts is the entire like set, the entire S2, then this
You mean the union of all these charts?
The union, right?
Yeah. Exactly. Intersection is like intersection, Yeah, the union would be
what this, and yeah, if the union, so if like U union V ... like this equals our like entire sphere, then this is a atlas, and there's like a fancy I don't know that.
Yeah.
So the atlas is like a collection of these charts, and then and then now we have this phenomenon, which is like if we have like our Earth, the real world, right, and we have some whatever curve on it, like okay, this is this too much? This is more than a summer.
Yeah, we're getting like into the whole thing, but
okay, yeah, let's not get into that. Or actually yeah, sure, I'll just
are we really close?
Yeah, just
what gets us really close to differentiable structures.
Yeah, exactly. Like this is a good transition to differentiable structures. Okay, so if we have some curve on our Earth, and then we want to see whether this curve is continuous. Well, let's say we call this like actually no, let's not call that. Let's call it what's the gamma symbol? it's that, right? Yeah. Okay, so we have so then we can and then we have our chart, which is U X. So then we can we can map our chart, our gamma to our wait, was this the notation that this is in? No, it's not X of U, it's X of gamma. This is in, no,
This is
is in, this is, okay.
it's either in U or a subset of U, something like that.
Yeah, something like that. And then like, right, and then,
Or no, this would be a subset of X of U, I guess.
oh yeah,
Probably something like that.
yeah, something like that, right? And then yeah, and then we can like test if our yeah, wait, and then like we have the, oh actually no, that's not how we do it, never mind. I messed up. How we do it is we have our real world, or actually not, so here is our sphere. There's a path, wait a second. Okay, you know what? I'm confusing myself. But anyway, it's why is it that?
Wait, hold on. First of all, what is gamma?
Gamma is
How is it like? What is it? It's a map from what to what?
the map from, it's a map from this the sphere to the U. Wait, no, that's not.
It's actually a map. I don't know if I should give it away.
Just give it away.
Yeah, okay. It's a map from R to M.
Oh, wait.
Or
Oh
I
my
think it's a
God.
subset of R to M, I guess. Like
Yeah,
0, 1 to M.
Yeah, because that's how paths are defined in things. That's how paths are defined, right? You just,
Yeah,
that's like
exactly.
this would be, it's like the start point would be 0 and the end point would be 1, and then like,
Yeah, exactly. Now you're getting
yeah.
it. Yeah.
Okay, yeah, okay, this is why space repetition is good. I seen it now.
Yeah, okay. So then
Okay, yeah, so then you have the R gamma to the subset of M, right? And then, or like, let's say we call this subset U, and then we take the, we can put it through a chart actually, so then this doesn't apply anymore. We can use our, we can use the map to map it to a chart, so like a section of the chart, the X of U, and then the, so then like if this was our map, like we were mapping the gamma on here, we will like see some like image of gamma after X on our chart, and then this actual curve that we are observing is X after gamma, right? So it's X after gamma, and because of like the nature of what it means to be like a manifold, or like what it means to be a chart, like this has to be continuous, like the chart,
yeah, the chart
thingy.
transition map.
Yeah, no, this is not the chart transition map. It's not going from a chart to another chart, right?
Oh, right. Sorry. No, it's not. What am I saying? It's the chart map.
Yeah, the chart map.
It's a chart map.
The chart map has to be continuous, and the composition of continuous curves is continuous. So if this, so if gamma is continuous, then this is also continuous. So which means that we can make observations about our real world without like actually looking at the real world. So if X after gamma is continuous, we can conclude that gamma is continuous. But what we cannot do is assume something like if we see that X after gamma is differentiable, like we cannot conclude that gamma is differentiable, because this guy over here can like mess it up. So oh no, what do we do? That's why we need differentiable structures.
Yes, and that's a good segue. Here we are, differentiable structures.
Yay, okay.
Because that didn't work.
Yes. All right.
I don't know what that message is, but I guess we'll go ahead.
All right. Okay, let's go. Okay, so before we talk about differentiable structures, okay, so we need some, before we can get into the meat of this, we need some definitions, like always. Yeah, gotta go through the boring stuff, I guess. So let's say we have the two charts, U, X, and V, Y. Okay. Yeah, so then we're gonna define that these two charts are C0. Yeah, okay, should I even talk about C0?
We can skip C0 because that was last time, right?
Okay, define these two charts are C1 or actually, let's just go straight. These two charts are flower
Yeah, flower was
compatible.
interesting.
These two charts are flower compatible if either or like either U intersect V, well, they have no intersection, or that U or actually the way he put it was like, or if Y after, or if U intersect V is, boy, why did I do is not equal on top? This should be
Wait, are you
if
writing
your
flower compatible or is this?
yeah, flower compatible. So either their intersection is empty or their intersection is not empty, and their chart transition map, which is Y after X inverse, is flower condition.
Flower condition. Okay, and then and then the flower condition depends on
Okay, and
what?
then also we also define a so like some atlas, how do I do this? Some
The A.
atlas A close enough is a flower atlas.
Okay, so if any chart is
yeah,
actually no way you're writing that.
Yeah, if every chart in the atlas is flower compatible. I don't need to write that.
Yeah, you don't need to write. If every chart satisfies this, then the atlas is this.
Yes.
If every chart, yeah, I realize I should say that out loud because like the video probably has like lag with when I write and when it pops up. But oh well. Yeah, if any two charts are flower compatible, the atlas is flower compatible. Cool.
Yes, and okay, yeah. So now okay, and also a atlas is maximal if like for yeah, an atlas is maximal if for every like C like no, not for every C, for every let's say U every chart in the atlas any for every other chart Y that is flower with UX so is, or actually not, we'll need every is, or actually maybe we do every, if it is compatible with flower compatible with U, then it is in the atlas, the implication.
Ooh, okay. So a maximal atlas has, if you have one chart, then take all the other charts that are flower compatible and then put them together, and that's the atlas. That's a maximal atlas.
Yes.
So nothing there should be maximal atlas is like no flower compatible charts left behind.
Yes, exactly. That exactly, you got it. So
all right.
Okay, so now what is flower compatible?
Yes, the big question.
Oh, c'est quoi la fleur? Well, say it could be, for example, there is a C0. So flower can equal C0 compatibility, which is the definition that two charts, or actually two the which is the Y after X inverse is continuous. Then we have the flower. When this is like very redundant and like trivial condition, because by the definition of a chart,
that's always true.
Yeah, it's always
right, because chart maps are always continuous.
Yeah.
So the X is continuous, the Y is always going to be continuous, so Y after X inverse should always be continuous.
Yeah, and then there's the flower can be CK, which is defined as the Y after X inverse is differentiable K times, and X after Y inverse also is, but like, I don't know, that's redundant to say, but like, and
But what were
Yes.
you gonna say though? You don't have to write it then if it's redundant. What are you gonna say?
Oh, so it was like, I think the conditions was like has to be different. So the y after x inverse has to be invertible, has to be it was invertible, has to be 1-to-1, and okay, yeah, but like the continuity already implies the invertible and the other 1-to-1 stuff, right? So I don't need to
True.
say
So it's
that
fine.
again. Yeah, so you just have to say it's differentiable k times.
Okay, cool.
And then flower compatible can also be C infinity. And what this means is y after x minus 1 is differentiable infinity times, which is like it's like the functions that you can like always differentiate, and there's like
So like you can take the derivative and then you can take the derivative of the derivative and then
yeah,
you can take, and you just keep doing that.
yeah, exactly. And like in like high school calculus, it would be like any polynomial function is C infinity is differentiable infinity amount of times, because like when you take the derivative of a polynomial function, it's another polynomial function, and then you just keep taking the derivative of it until you get like the derivative is 0, because you get to the lowest order, like right, like because every time you take the derivative of a polynomial function, you lower the degree by 1. So
Yeah, until you'll
yeah,
eventually get to a linear equation.
yeah,
Then its derivative would just be the slope. And then derivative of like the slope, which is a constant number, would just be a line.
yeah,
And then you can keep taking, or like the derivative, wait, no, hold on. With the
yeah,
derivative of a constant number would just be 0. So then you would end up just having y equals 0, and you can just keep doing it like
yeah,
y equals 0, y equals 0. Like all the derivatives after that are just y equals 0, but they're still differentiable. It's just the
exactly.
derivative is y equals 0.
Yeah, and then C infinity is also called a smooth. So like a C infinity atlas would be called a smooth atlas. So like it's very,
Oh, okay.
and I actually kind of like that because it meets intuition. Like, you know how like when something is like not differentiable, it would be like I don't know, if it has something like this point is like not differentiable, it's not smooth, or like, or if something was like, for example, if we have some curve like this, and then like here like the slope is nothing, like when you differentiate this, it would be like here we have the slope that's going down, but then here the slope is nothing. So like I don't know, even though this is differentiable, this is not different. I don't
Wait,
know.
yeah.
Yeah, like
Hold
you
on.
know,
Yeah,
something
I'm
that's
actually not
not
so familiar
smooth.
with calculus. Like, what is a case when you like you can take the second, like you can take the second derivative, but not the third derivative, or something like that? Like, at what point?
Oh. Okay, so like if you have something like, or let's use this. So like if you have something like you have like a straight line, right? And then suddenly this, let's say here's like a section of a parabola or something, it's smooth here, so like here there's like some invisible break, like here this is a linear, this is a quadratic, and then when you take the derivative of this, like it becomes, so here since this slope is linear, we have a constant slope, so it just be like so let's say this is like at point X. So this is point X,
Aha.
right? So this is a constant slope. This is some positive number. And then, but here, this is a quadratic thing. And the derivative of a quadratic is linear. So then the slope is linear starting from here. So at this
Ooh.
point, it is, you cannot take the second derivative of this function, but you could take the first derivative.
Ooh. Okay. That's interesting. Okay, so that's how. So that's why you might not get like you can't just have infinitely differentiability for everything.
Mm,
Okay, cool. I didn't know that actually. I didn't know of an example where that happens.
mm.
All right.
Yeah, this is
What else?
interesting. Okay, and then okay, yeah, so then there's also okay, let's switch back. There's also flower. Yeah, I'm not drawing very nice flowers. Flower can equal he calls it like, what's it called, like analytical something. But like it was like, yeah, I don't know, but he doesn't mention it, like it's like there's some there's some functions are called analytic functions, and what that means is they can have some Taylor something at every point of the
Oh,
function.
Taylor expansion.
Yeah, Taylor
Do you know what that
expansion.
is?
I have no idea. Oh yes.
Okay.
Yeah, so it was like C omega, right? C omega equals the transition maps, like the y after x inverse is analytic. I don't know. Do you know what that means?
Kind of. So I think it's related to, I think, Taylor's series, which is like when you have a polynomial, like not a no, when you have any real function, like when you have a function from like R to R, you can, I guess, approximate it as a polynomial function. Like for example, sine of x, you can turn you can turn that into a polynomial function that's arbitrarily as good as you want. So you can have a bunch of terms, and the more terms you add, the more it can look like a, well, I don't know. Let's search this up actually. I wonder if I can Taylor expand Taylor series. Sure. 3Blue1Brown has a good video on this, but yeah, you can check it out later. Just the video on Taylor series. It's I can't explain it. I cannot explain it as well as he can. That's for sure. And it's only a 15-minute video, so yeah.
Cool. All right, send it over. I'll check it out.
Yeah, I'll send it. I can send it right now, actually. Let's see. Taylor series. Oh, it's actually 20 minutes. Never mind. But
all right, that's good.
Close enough. Not as long as everything else we're doing. Oh, that's an ad. I'll send it on the Mafia Slack, I guess. Okay, there. Yeah, you can check that out later.
Awesome.
And then flower.
Yeah, and then
complex.
Yeah. So the analytic is a stronger condition than being smooth. And then there's also flower can equals what was the symbol for this? It was just complex. And what this means is like I guess the intuitive idea behind this is that, like, let's say we have some, we have the manifold, like the manifold has a dimension, like it has to be an even number dimension. So let's say it's like 2-dimensional. Then the idea would be like the chart transition map y after x inverse. This would go from R2 to R2, and like said theoretically, the complex plane is like isomorphic to R2. So it would sort of be like the intuition is like, if instead of mapping from R to R2 to R2, we turn this into like the Cartesian coordinate plane of like so like the R2 would be like let's say like something like R, I don't know, R, and then like we turn this into the first real number of the Cartesian product plus R2I, so we turn it into a complex number. Then this complex function would be differentiable.
Okay.
Yeah.
So it's about differentiability of like complex functions, I guess.
Or was it about yeah, it was about differentiability, and this is a stronger condition than being smooth, because like if a complex number, the function is like, I cannot visualize a function that goes from complex to complex because that would require 4 dimensions, right? But I guess you can imagine like you have that from Schiller put it was like you can have the points coming at it in many more directions, right? Okay, but anyway,
it's very difficult to do though. But that's interesting also. Like we had C infinity, and you would think that's like the best, like the most strong condition, but there were actually 2 more conditions that were stronger, which was C omega and C complex or whatever. I don't know what the symbol was.
Yeah,
so that's interesting.
The actual way he defined, okay, so to be more precise, it would be like if a map goes from R2 to R2, and this is a continuous map, then it has to satisfy and so like this map, in order to be complexly differentiable, has to satisfy something which is like like the I actually don't fully understand what this means. Plus Vx. Wait, like what do Well, I just copied this, but I'm not sure what it means.
In
Oh yeah, no, it goes from oh, okay, I see. So it goes from xy. Yeah, so the R2 to R2 goes from xy, let's say to whatever, to the u of xy, v of xy, like this is, I guess this u and v are just the the components of the f, like how
I
there's like,
guess.
yeah, right, that goes to each dimension, right? Because like remember earlier he said something like you have some x that goes from r2 to r2. You can break this down into x1 that goes from r to r, and like another x that goes from r to r, and then like x equals the x1 plus x. I like this is not the exact notation.
Yeah, okay. I guess I get what you mean. It's fine. I don't think we're gonna see complex anytime
Yeah,
unless we do. If we do, that's like, oh well, we'll catch up on that then.
yeah,
But yeah.
yeah. So then like if we turn this into a function that goes from x, okay, let's erase some of this. Goes from x plus iy to the u of xy plus v of xy times I. So like, so then we were like, we're turning this function to this function, like
So it's more it's like complex now.
yes, and then this function is differentiable if du does there's something like equals dv of d,
Oh, these are partials, yeah.
yeah, these are partials,
Oh boy.
and partial u over partial y equals partial v over yeah, like I don't see why that's the case. Like I will have to take a lot of time to figure that out if we
Yeah.
want to. Yeah, but basically what he said is like if some real function that goes from like R2 to R2 satisfies this, then it is just as good as a complex differentiable function.
Okay, so these are called the Couchy Riemann equations, apparently.
Yes.
Damn. Okay, so this is a whole course about like complex. There's I like in the notes it says like if you want to know more, just take a whole course on complex analysis.
Oh geez.
So it's a whole deep thing. Um. So yeah, I don't think we can expect to fully get it right now. Yeah. Okay, it's fine. We'll just breeze past it for now, and if we need to, we'll come back and do Cauchy Riemann complex analysis stuff.
Cool. All right. So now there is a theorem that any maximal CK atlas where K is greater than 1 contains a, well, actually no, subset. There's a subset that is a C infinity atlas. So, and also any two CK atlases that contain the same C infinity atlas are identical. And like, you know how like yeah, these are maximal atlases, right? So what's it called? Like you can't always for any, so CK atlas is like you can always make a C infinity atlas by like taking out the maps in it that are not C infinity with each other.
So you might have like, okay, so you might have like a bunch of maps. Some of them are C infinity. Then there's a lot of other ones that are only like C2 compatible or whatever.
Yeah,
So if you take those
exactly.
C2 out, you can always get a C infinity in. Okay, interesting.
Yeah, and also this has the implication, he says that like from CK where K is greater than 1, like it doesn't make, or greater than equal to 1, it doesn't make a difference like whether like in this sense, like it doesn't make a big difference which K you choose.
Because you can always, because you only care about the C infinity one. So if you find one that's C in 1, you'll just be like, okay, let's just use the C infinity one instead.
Yeah, I guess that's the, I guess, yeah, or also because like you can always make them from each other, so
Okay.
yeah. And also okay, so then there's also another definition, which is incompatibility. So let's say we have our basic topology, which is the real number line equipped with O standard. And let's say we choose atlas 1 is a atlas that contains the chart, which is the entire the domain is the entire real numbers with the map, which is just the identity. And if you look at this, this is a C infinity atlas because there is one like the definition is like any two charts in it are C infinity compatible. So like the if you take the identity after identity, that is forever differentiable.
Yeah, that's true.
Yeah, so that's a C infinity atlas, right? And then also if you have choose another atlas, which is which same domain, but we have a different map, and we define this map as you map every number to a to the 1/3, so this is the cube root of it. This is also a C infinity atlas because the chart transition map would just be the cube root after the inverse of the cube root, which is also the identity. And
Oh,
right, because there was like no charts in it to transition from each other. So like I guess any atlas with one chart in it is C infinity.
right. But then again, because like there's nothing else to be compatible with because there's only one chart.
Yeah, exactly. Right.
But it's not, would it be maximal then?
Yeah, this would not be maximal, right? Because like there are, for example, something like some if we had here like the some map that went from R, or just I took every number to like I don't know to the like it's double, then this would also be C infinity compatible with this one, but it's not in it.
Okay, wait, so then hold on. For this theorem over here, does this have to be maximal?
Yes.
Yeah, okay. Because the idea was like you can always take stuff out to make it C infinity, but if it's not maximal, you might not be able to take anything out.
That's true.
Okay, yeah.
Oh
So
yeah,
that's
take
why.
things out and still have it be a full atlas, right? Because an atlas
Right.
has to contain everything. Yeah,
So
okay.
that's what, okay. Okay, cool.
Okay, so now if we were to make like we can't make both of these sets maximal. Okay, wait, actually, so but these two sets, these two atlases, they are so A1 and A2 are not compatible because like if we like take the union of these two atlases and make a big atlas, like this would not be C0 compatible, a C infinity compatible, or this would not even be like C1 compatible because like the transition map from this chart to that chart, so like that would be like, let's say that would be like I don't know X inverse after identity, or actually the other transition, like so the identity inverse after X, like well the identity inverse is just the identity.
Oh wait, don't you mean like identity after? So wait, hold on. We're starting at the chart in A2.
Wait, no, we're starting from a chart in A1 and we're transitioning here.
So we've got this, and we've got this is, let's call this like C2, which is an A2. So to go from here to here, don't we need to do identity inverse first?
Yeah, identity inverse first.
And then we go to X, and then we go from X.
Yeah.
Like then we do that. So aren't we doing, so wouldn't this be X after identity inverse?
Huh. I know, because it's like, any like chart, right? Any like we have some I don't know, so we have the real world, and then we have like a map X, map Y, and then to go from X to Y, we have to, it's always X inverse after Y, right? Like because we go, because
Wouldn't it be, because like, hold on, this would be U of X, this would be V of Y. So you want to go from U of X to V of Y, you have to go this way first and then this way, don't you?
yeah, so then you're doing X inverse first and then Y.
Yeah, so X inverse first. So why would you say X inverse after Y?
Oh my God.
Yeah, it's so
Oh,
true because you have to go from you have to read from right to left, right?
you have to read from right to left.
That's
Ah,
why it's
Jesus.
after I. Yeah.
Okay, my bad. So this would be X after identity inverse, which is just X, and the X, like if we were to graph this cube root function, it will look like that, right? No, not like that. And this is not differentiable because at 0, the slope is like infinity. Well, it's like approaching infinity. So it's so like the cube root function is not differentiable. So these two atlases are not even C1 compatible.
Oh, okay. Wait, this is the cube root function.
Yeah.
Okay, hold on. I want to try that in Desmos. Desmos. So it's just cube root of X,
Yeah.
right? And then it's at 0. It's basically infinite. Wait. Why is it's wait, hold on.
Wait, so like if you take X to the
Cube root. How do I write it on Desmos? How do you do cube root?
how do you do cube root?
Oh, can I just write X to the 1/3? That'll work. Yeah. Yeah, and then it's infinity it's basically infinity at 0, right? So the cube root is not differentiable. I thought it would be like, I thought it would just be like 1/3 X to the, like 1/3 minus 1.
-2/3.
Yeah, exactly.
Okay, wait, so 0? What's 0 to the -2/3? It would be, no, but then you see to the negative, you have to do 1/0 to the 2/3, which is 1/0.
And that's where the problem is.
Yeah.
Oh, that makes so much sense. Okay. So that's why that's not different. That's not, oh, okay, that's cool.
Wait, so any function, any function where it's like X to the A, where A is less than 1 is not differentiable because because when you exponent, the -1 is negative, so you have to do 1/0.
Right. Okay, cool.
Cool. Okay, yeah. So now we see this. It's like, look, even the real number line has two non-compatible. Oh yeah. Okay. So yeah, if we were to like maximize the A1 and the A2, like we get all the charts and their chart maps that are C infinity compatible with it, we can like make a maximal atlas out of both of them, and then it's like even the real number line has at least two different differentiable structures, right? Like these two different maximal atlases, and it will be like, oh no, which one do we pick? The sort of thing.
Okay.
Yeah, so we'll get to that. We'll answer that question later at the end of this lecture.
Which one do we pick? Oh, wait a second. Is this the lecture oh wait, no, I'm not sure. Okay, I don't know, just go ahead then.
All right.
Because I'm thinking like, is this the lecture I'm thinking of? I don't think so.
Okay, so we're gonna have to define something else. So the definition of a Ck manifold.
Now we're talking about differentiable manifolds.
Yeah, so a Ck manifold is a some triple of a set, a structure, and a atlas.
And that structure is just the topology, right?
Yeah. Oh.
Oh no, the siblings have arrived.
弟弟，我在个 meeting 里，我现在不吃饭，好吧？你告诉妈妈。All right. He's telling me to eat. But already. Yeah. I'll eat after this.
Okay. Wait. Actually, I just realized, like, how is the Zoom not like kicked us out yet?
Oh, Zoom like a few minutes ago just randomly gave me a message and was like, hey, we're giving you a gift today. We're not gonna have your your thing expire, your meeting expire after 40 minutes. I
Oh,
don't know.
thanks, Zoom. Very cool.
Oh
All
wait,
right.
someone's at the door. Give me a sec.
All right.
我在个 meeting，你告诉妈妈，你现在不要跟我说。All right. Okay, that was my sister.
All right. Okay.
Yeah. Zoom, I don't know. Zoom is feeling kind today.
Nice. All right. Okay, differentiable manifold.
Yeah, so it's this triple, which is basically a topological space, but you just add on the atlas to it. Yeah, okay, so then this A is a maximal CK atlas. Okay, so now if we have two manifolds, or we have two CK manifolds, we have the or two differentiable manifolds, we have the MOM atlas M, and then we also have NON atlas N. So then we have some map phi between them. Then we say that this map phi is differentiable. Well, a CK differentiable if let's see, if for every for some UX, so some chart in the M atlas and some chart in the N atlas, we have Y after phi after X, well, Y inverse is differentiable. I might have mixed up the afters.
No, I think you got the afters. Wait.
Wait.
I think it's X inverse.
Yeah,
and then
X
the Y is
inverse.
just Y.
Yeah. Okay, there. And so yeah.
How much differentiable?
CK differentiable.
So like K differentiable basically. Because CK is like CK is like the wait. Actually, hold on. So CK is when you have a map from a manifold to a manifold. But K is when you
the
have
number.
Yeah, K is like, yeah, and K is like, you would usually say the map is K differentiable if it's like from the real numbers to the real numbers. Which it is.
Yeah, exactly. Yes, because this entire thing is a map from real to real something to real something.
Yeah.
Yeah.
Why is that? Actually, hold on, go to the next screen, I guess.
Okay, why is that? So now we have our big diagram of differentiable structures. This is like the meat of this lecture.
Oh, yes, it is. Yes, it is.
All right, so we're gonna draw that again. So we have whoops. So we have the actually, this is actually not entirely accurate. The phi goes from M to N, like just
the topology is kind of like it assumed, I guess, that it like the topologies comes with it, I guess.
Yeah, and also like if you think, how the hell do you define a map that maps like a topology to a topology? Yeah, right. So yeah, because like by definition, the map is like
from the set to the set, and then when you ask like, is this map continuous, then you say, okay, let's look at the topologies and see what happens to them. Or
exactly, right? So like we define continuity using the topology, although the map only goes from set to set. So similarly, we define differentiability using the atlas, even though the map only goes from set to set.
Ooh, okay. Very cool.
This took me like 30 minutes of rewatching the lecture to figure out.
Yeah.
All right. We're going to draw our big diagram of science, not science, well, but
math.
Of math. So we have our M and we have our N, and they have this phi map between them. Okay, and then so let's say we choose some chart we choose some chart. So we have U. Oh, actually, you know what? We should not do this. We're gonna not take our entire M. We're only gonna take a section of the M, the U, and we're gonna take a section of N. Let's say V, and then the V and the U are like are part of the charts. So like we have the
Mhm.
U X is a chart and U V is a chart, and then so using our chart map X, we go to X of U, and this goes to Y of U, right?
Or Y of V.
Y of V, right?
Is
This goes
it-
to this goes to Y of V, and yeah, and then this is a subset of R D. This is a subset of R E. This would be a different dimension.
Could this be a different dimension?
Yeah, I think,
I guess it could. That's
uh-huh.
cool.
Yeah, and then and then this thing would be, so yeah, if we would go backwards, right? We go from X inverse and then phi, then Y. So it would be Y after phi after X inverse.
Let's go. We got it right this time.
Yeah.
Yeah, okay.
Okay. So now using this, okay, so here's the thing, right? So we are trying to find the differentiability of phi, and by definition, because because the U of X, like this was chosen from, this is an element of our atlas, and this atlas is CK compatible, right? This means that
But CK compatible is when you have two charts. The atlas would just be CK.
the Alice would just be CK, right? Okay, so it would good catch.
Wait, is that is? I'm not lying when I say that, right?
I'm pretty sure. Yeah.
Okay.
Yeah.
Yeah,
So
I'm pretty sure it's just the atlas is a CK, like a C infinity atlas. Yeah, exactly. So CK. Okay.
yeah, so it'll be CK, right? So which means that like this section, the Y after X inverse, like by definition, it has to be CK, like it has to be K differentiable, right? Yeah, because of the chart transition map has to be K differentiable by definition. So so the composition of two K differentiable maps is also K differentiable. So since we are, I guess, okay, we're not exactly composing Y after X inverse with phi, though. But like, I guess you can still see why if Y after phi after X inverse is K differentiable, that implies phi is also K differentiable.
Does it imply that, or is that just how we're defining it?
Huh.
It's like, what does it mean to say a map from a manifold to a manifold is differentiable?
Because we're only talking about the map from the, like here, it's like from the set to the set, like not from the entire manifold. Like we're using the atlas only to define differentiability.
Mm-hmm.
Like I think we went into this lecture with
Because we only know, like, if we have a map from, because the only thing we know how to call differentiable is a map from RD to RD, or RE, I guess. I can't use E. E is
yeah, E is Euler's number.
E is forbidden. I guess. Yeah, but like that's the only thing we know what to call differentiable. So now we're like, okay, what do we say is differentiable for a map from M to N? And I think this is how we just define it.
Oh, wait a second. Oh, wait. So we are defining differentiability on non-RD to RGs. Yeah, let's
to be that. This.
To be this, right? Like, oh, so we are, yeah. Oh, yeah. This is what it means. Like
that makes sense, right? So like now we're saying if this is differentiable, then we'll just say that that is also differentiable.
Ah,
if
okay.
Y after phi after x inverse is differentiable, then we'll call phi differentiable.
So this is a definition. Oh, so it's like, yeah, this is where he says like, this is manifold philosophy. We define things in the real world by mapping them to RDs to like RGs.
Yeah.
Yeah, but this isn't enough because you have to prove that this is well defined, right?
Yeah, because again, this is the definition, but is this a good definition, I guess?
Yeah, right. And like, so here we have chosen some arbitrary u and x from our atlas. Like, so we have to make sure that whether this is differentiable or not depends on the atlas that the particular chart that we have chosen.
Right.
All right, cool. So yeah, okay. So yeah, so we have to make sure it's well defined, so it doesn't depend on the arbitrary choice of chart we pick. And so let's say we have a so now we're going to like so let's say we have some other chart that the map is x twiddle, and then so it would be here would be x of u twiddle, which is
Well, actually, this would be x twiddle of u twiddle.
yeah, x twiddle of u twiddle.
Wait, no. This would actually be x twiddle of u, because the domain is still u.
Right. Yeah, okay, that makes sense. Yeah, still has to be x twiddle of u. Yeah.
Oh,
Yeah.
where did the twiddle go? There we go. Okay.
Yeah, or it would be x twiddle of u twiddle, like intersect u, because
Oh, right. Wait, hold on.
yeah, because like this it's not like because since we just have to make sure that wait a second. Yeah, the x. Okay, wait. Yeah, we have to make sure that that these thing, what's it called? Just the curve. Wait, no.
Wait a second. Does that mean this actually has to be u intersect u twiddle, and then
Yeah.
this is okay. U intersect u twiddle now.
Mm-hmm.
And
Okay,
then
same with the other side.
yeah, v intersect v twiddle. Oh, actually, yeah, you can.
Yeah, you do it.
Oh, okay.
And
And
then
then you can do it here, team effort. V intersect v twiddle. Yeah, okay. Lots of twiddles. Are they called twiddles? I think they're called like tilde, but I guess in no way, but he calls it twiddle. I don't, maybe they call like different things in different countries. I don't know.
All right. So this is v intersect v twiddle. And then we have the same thing here, which is y after y twiddle after phi after x inverse. And then what this so now yeah, so what we want to verify is it's consistent, right? So so now we have to show that if this is differentiable, then this also has to be differentiable. So what is the thing that goes from like here to here? Well, it would be this. Now this, we are going between two charts, right? We are going between so this would be a chart transition map. So the chart and the chart transition map is just the y twiddle after y inverse. And now the great thing is that this chart transition map must be CK differentiable because of the way that our maximal CK atlas is defined. And similarly, this is going to be messy. This also.
Oh, right. You can erase like that part, I guess.
No, it's good.
Yeah, that would be okay. Yeah, it's fine.
Twiddle after x inverse. And this this will also have to be continuous, right? And so and because the composition of continuous maps, I mean of differentiable maps is also differentiable, then Then if
Okay, wait, hold on. How do we know that how do we know that x twiddle and x are both k differentiable? So we know that k is differentiable, right? Because that's what we're talking about. Or sorry, we know that x is k differentiable.
no,
How do
we
you know
do-
that x twiddle is also k differentiable?
no, we don't know if x is k differentiable, but like we know that x twiddle after x inverse is k differentiable because this is the chart
Oh, right,
transition
because that's
that-
not a thing.
Yeah, that goes from, and this goes from RD to RD. Like it goes from the same dimension to the same dimension.
Right. Oh, yeah. This is so. This is a subset of RD,
Mm.
right? And this is also a sub. So this is a subset of R. What did we use? G.
Yeah.
Okay.
Yeah, and then
Why didn't I
this,
use F? Oh, because F is like function. I don't know. There's so many letters are gone. Okay.
yeah. Wait, so
And how do we know that x twiddle after why is x twiddle after x inverse k differential ck differentiable again?
Because that's how this CK differentiable atlas is defined. Like for this atlas to be
Ooh.
CK, all the chart transition maps must be.
Right. So it came with the atlas that allows us to say that. Okay.
Yes. And this is what answered the question we had at the beginning, which is well, not at the beginning. Well, yeah, the first thing the one that I was talking about in the previous lecture, where if we have the gamma, the real world gamma, and we map it onto a chart, if the chart is continuous, we know that gamma is continuous, but we don't know that it's differentiable. But if we restrict ourselves to our only the charts that like only the CK atlas, then we can verify that our chart curve is differentiable, implies that the real curve is differentiable.
Okay. Now how do we know? Okay, so we've seen all this. We know that x after x inverse is differentiable. We know that y after y inverse is differentiable, right?
Mhm.
Now, how does that prove that these bottom things are differentiable, the ones that I'm underlining in green? Or squiggly underlining, I guess.
Oh, we're not proving that differentiable. We're proving that given that this is differentiable.
Given that, right? Okay.
Yeah. Then so we're implying that given this is differentiable, it means that phi is differentiable. Actually, we're not proving that. We're defining that.
Yeah, and then we're
proving.
And what we're doing right now is we're trying to check if it's consistent. So we're, I guess, proving that given y after phi after x inverse is differentiable, can we be sure that a y twiddle after phi after x twiddle inverse
Yeah,
is differentiable?
exactly.
Okay, so how do we be sure of, how are we sure of this? How are we sure that this is consistent?
How are we sure that this is consistent? So we know this is differentiable. We know that is differentiable. And we know, so if this is differential,
Okay, go to the next screen and I think I can show you because it's like written in my notes. I can start showing. Okay, wait, so we're talking about y twiddle after phi after x twiddle inverse, which is equal to wait, well, how did this work? Y twiddle is okay. Wait, I don't know if did he say this in the lecture? I don't remember if he did, but what he did, what it says here in the notes is it seems like okay, hold on, let me just like write this here and then see if it makes sense.
All right.
So there's a y twiddle, and then it looks like in here in like this position, we're inserting a y inverse after y. And apparently you can do that because this is just an identity.
Yeah, yeah.
Right. And then And then we still have this phi over here.
Mhm.
And now before the x inverse, I guess we can, or before the x twiddle inverse, we can insert an x inverse. Wait, what?
Yeah, x inverse after x, right? Like,
I guess so.
yeah, and then this, yeah, I see it now, because like we know that, and then no, and then we need to, yeah, x twiddle. So we know that x twiddle after x, this is differentiable. We know that this part is differentiable, so now we just have this part left.
Wait a second, but we can't do x after x twiddle.
Wait, what do you mean? Oh, it has to be, oh yeah, so then you have to flip it. We have to like, it would be like here, it'll be x inverse here. So x inverse after x twiddle is differentiable.
Wait, you still can't do that. Hold on, because go back to the previous thing.
Yeah.
So x twiddle, yeah, x twiddle takes you over here. So where can you go from here? You can only go this way.
Yeah, so x twiddle after x inverse would be
Oh wait, you can do x twiddle after x inverse, right? That's this thing.
yeah, it's this thing. Yeah, exactly.
Okay. So
Yeah, and same here, right? Same, it would be
so then we have to turn this into x twiddle after x inverse somehow.
yeah. Well,
Wait,
well,
because
x,
what it says in my notes is something weird.
wait, no, but x inverse after x twiddle is also continuous, because I mean differentiable, because that's also a chart transition map. It's just a chart transition map in the other direction.
Exactly. So like we're trying to leverage that.
Yeah,
But
right.
what it
So
says in my notes here is that we do so phi, then we do x inverse, and then something like this. X twiddle after x inverse, and then inverse the whole thing.
okay.
Does that make sense?
Okay, wait. Wait, I don't think we need to do that though. Like, what if we just do like, what if it was just x after x inverse, and then here we go back to
No, because
after
like,
x twiddle.
oh,
Like because you see this is a chart transition map, so this is differentiable. This is also a chart transition map. Actually no.
actually, wait, hold on. This is supposed to be, hold on, wait. This is supposed to, the x inverse, the y inverse is supposed to be here.
Yeah.
And then, oh, what we want, hold on, wait, go back. We want to have this thing in here somewhere at the bottom.
Yeah, the thing at the bottom. So the thing at the bottom is just this, right? No?
Yeah, but there's an x inverse.
Oh, frick.
So then, wait, erase the, I can't erase this thing.
Erase which thing?
The x inverse, the two x inverses in a row. Wait, just erase like the whole last few terms. Okay. All right. So we want to put this in here.
Oh, wait. Because this thing is x inverse. So like we can do the x twiddle inverse here. So this is not inverse, and this is x. This is just x. No, this, okay, never mind. This is inverse. So this is still the same thing, no?
Oh, there we go. Okay. Now we've got it, I think. X. Yeah, okay. X inverse after x twiddle inverse. Okay. Yeah, I think we can do that.
Yeah.
And then,
yeah, and because the composition of differentiable maps is differentiable, so this is differentiable, that is differentiable. So which means that if this is differentiable, then that implies that this is also differentiable.
okay, let's go. We did it. Okay. Epic. Nice. The proof is done.
Yeah.
So our definition of differentiability is consistent. Let's go.
Yay. Okay, so what's left? Diffeomorphisms.
Aha. Okay.
Okay, yeah. So actually, it's pretty simple. If a
Wait, do you want to do a new screen?
actually no, I think I'll just go back, because you see this thing, right? We have this thing where we have the phi that goes from m to n, where we have
Okay.
the the Ck manifold, and if there exists a diffeomorphism that goes from, well, no, if this phi that goes from n to m is differentiable based on the definition we just gave, then phi is a diffeomorphism.
Oh, which means that.
And if there exists a diffeomorphism between these two Ck manifolds, then these two Ck manifolds are diffeomorphic.
Yo, that's so cool. A lot of diffeos and homeos that we used before. That's epic. Diffeomorphism, diffeomorphic map. No, diffeomorphic. So the manifolds are diffeomorphic. The map is a diffeomorphism because it's differentiable.
Exactly, right? So we
Oh.
started with our sets that have isomorphisms and can be isomorphic, and then we added some structure to make the topological topological space that have homeomorphisms and can be homeomorphic. And now we have added some new structure, which is the differentiable structure, the title of this lecture. And we have the structure preserving maps that are the diffeomorphisms, and the diffeomorphic means like differentiability, like isomorphic or whatever. And that is our mathematical foundation of structures of stuff. Very cool.
Awesome. Okay. Is there anything else?
Okay, yes. So one more thing, which is to answer the question we had earlier, which was like we have the R to R. Oh no, we have like, even for the real number line with O standard, we still have multiple. We had multiple what's it called? Multiple the maximal C infinity different C infinity atlases, right? And then the question of which one is real, which one should we choose? Well, if two like Ck manifolds are diffeomorphic, then they are like basically the same. Like they're like, we don't need to distinguish between them. And good news for us, our two where were they? Yeah, this one. So this atlas, these two atlases made maximally, they are diffeomorphic to each other. So that solves our problem.
Oh, okay, yeah, that's epic.
Yeah, so that solves some physics. That's like this. He says this has like physics implications to physics. And it has also been proven, like some remarkable proofs, like these are pretty good, impressive breakthroughs according to Schuler, that for any like d-dimensional I'll just write d-dim manifold. So if if the D is 1, 2, or 3, then that means for every manifold, there exists only one unique smooth manifold, meaning a Ck manifold. Yeah, so for every topological manifold, there is this one unique smooth manifold. This is a theorem.
Okay.
Yeah, this says topological manifold. Okay, and then for D equals D is greater than.
Uh-oh. Why are we skipping over 4? Okay, wait, go ahead. I think I know why.
Yeah.
I think I'm starting to remember why we're skipping over 4.
Oh, yeah. Yeah, so for D is greater than 4, there is a finitely many. So for every topological manifold, there exists a finitely many smooth manifolds. And this has a very profound impact on physics, because like, for example, like string theorists believe like a universe has like what, like 21 dimensions or something. Like if the universe does have 21 dimensions, then like theoretically, like since this is finitely many, like we can list out every single one of them, right? And since we can list out every single one of them, like in theoretically we can like verify like because we're trying to find out which one of these
Yeah,
differentiable
which one is the
structures.
universe?
Yeah, which one's the universe? So then we can like empirically do some experiments, do finitely many experiments to test like which one is the theory of which one is how the universe works. And yeah, okay, but unfortunately for us, for the special case of b equals 4, there
Which
is
is unfortunate, which is space-time, right?
yeah, which is our space time. There is a uncountably
Oh
infinite.
God. I always found this like really funny. Like it's not even countably infinite, it's just uncountably. Like it's not
Yeah.
even innumerable by their natural numbers. It's just you have no chance.
Yeah, exactly. There's an uncountably many smooth manifolds per topological manifold. So this is like for our
Wait,
universe.
I would say I think so the way it's written in the notes, like instead of saying like there exists like one unique smooth manifold or like uncountably many, like they're saying like differentiable structures. So there's like there are uncountably infinite differentiable structures that you can impose on the manifold, I guess.
Okay. I think in the
Yeah, I guess
lecture he says smooth manifold.
oh, I guess it doesn't really matter then. But yeah, okay, uncountably infinite. That's unfortunate.
Yeah, so we'll have to do an uncountably many number of experiments to test, right? So it's like it's also in physics. It will be like what if all of our, I guess, laws, like our worldviews of how physics works is wrong because we chose the wrong differentiable structure.
Yeah, that would be sad. Wait, so actually, I wonder like how do they so what do they actually do then? I think they don't like they're like, okay, we can't just count it by we can't just do experiments to figure it out. We have to like be smarter now when we come up with which structure to pick.
Yeah, I don't know how they do
And
that.
I think we'll find out eventually, hopefully.
Oh, I
Because
hope.
I don't think we've like so far like what I've done up to like lecture 12. I don't think there's like an answer we got for which differentiable structure is Einstein's spacetime.
Oh, okay. I'm writing this down. I want to know the answer to this.
Which differentiable structure do we pick?
Structure is like, yeah. Okay, damn.
That's really weird to think about. Like you'd think that each dimension is just like it's just another dimension. It's not that big of a deal, but it's like crazy.
Now, why 4? Like, why was the universe created? Why was math created this way? Well, the
Yeah.
universe created math. So actually, no. Did the universe create math, or does math exist abstractly outside of any universe?
Oh boy. Another thing too is like I think once David said that, by the way, I like how it says here for D is like for I think 1, 2, 3, there's like yeah, for 1, 2, 3, there's like only one unique one, right? And then for D is greater than 4, there's finitely many. I think once David said that, he searched it up, and then it's like so it looks so random. Like it's like 5 is like there's 4 different options, 6 there's like 5 different options, and then 7 there's like 21 different. Like I don't know. It was like crazy random.
Also, they're not even big numbers. But
yeah, and then some are like 900. Like no, but like sometimes they're big numbers.
Oh.
But most of the time, sometimes they're small. So it's like crazy random. So I don't even know. It looks like super random, and then like 4 is even more random. It's just it's uncountably infinite.
Yo, you know what? This should be the new random number generator. Like how to make random numbers efficiently. You just
just pick a manifold. Just pick D is greater than 4 and like pick a random number, and then just be like, okay, how many possible smooth manifolds can we have?
Yeah, exactly.
All right. Okay. So
All
now
right.
what?
I think that's the whole lecture.
Okay. Yeah, I think that is. I think there's something about Betty numbers, but it's not really.
Oh yeah. Okay, yeah, sure. I'll go over that too. It's basically like so for this uncountably many case, this is the case of if these are non-compact manifolds. And then for the other case, if we have compact manifolds, so like, okay, so then there's this thing, which means, and So and Betty number 2 is greater than 18. And so what the Betty number means is basically like, so like the Betty, so the B1 is the number of 1D holes, and then B2 is the number of 2D holes. So it's like it's like basically like, you know, a torus, like this is one hole and this is a two-dimensional hole. And so
Yeah.
so like we, you know how there's like the Bretzel thing,
And it
right?
has like 3 two-dimensional holes.
Yeah, so for this, yeah, Betty number 2 is 3, right? So basically you can imagine a Bretzel with 19 holes.
Yeah.
Yeah,
Okay.
so for a Bretzel with 19, okay, but Bretzel would be a 2D manifold, so not exactly, but like something similar, a 4D manifold with 19 two-dimensional holes. There is a countably many. There's
Wait,
a,
so if it's greater than 19?
yeah, if it's greater than 19 holes, there is a countably many smooth differentiable structures. And
Ooh.
this seems pretty random too, 19 holes.
Yeah, I know, like why 19? But also this countably is still infinite, right?
Yeah, it's still infinite.
And this,
So
like, if D is greater than 4, or D is equal to 4, so
that, yeah, this is still D equal 4.
dim's equal to 4 manifold. So not really a Bretzel, I guess, but like a 4D Bretzel.
Yeah.
I know, but Bretzels are technically like 3D shapes, but 2D manifolds.
Yeah, so
But
4D
yeah,
manifold Bretzel. Too bad we can't visualize that.
yeah. And then for a dim 4 Bretzel, if Betty number 2 is greater than 19. Okay, so that's better than uncountably many, but it's not it's still not great. Still
Yeah.
countably infinite.
All right,
Okay.
Avneesh, I have a question to ask you.
Okay.
Do you think the universe has more than 19 holes?
Oh no. I think it actually, does the universe have 2D holes at all? Are black holes? No.
Oh, well, what?
Are black holes Betty holes, or are they like a different thing? No, wait, I'm pretty sure they're different things, right? I have no idea. I have a feeling the universe is just going to make things harder for us and have more than 19 holes.
But if it has more than 19 holes, it's easier for us. No.
Oh wait, yeah, then it has less than 19 holes. Yeah, whatever makes it harder for us, that's probably what the universe did, just to
Yeah,
like
makes sense.
piss off humans.
Yeah, the universe was created to piss off humans. There you go. That's the meaning of life.
Yeah. What are the 2D holes then? Are there like, because intuitive, like I feel like there's 0 holes. Is there a hole? Are there holes in the universe?
I mean, like, I guess if you lived on a torus, you wouldn't be able to like see the hole, like you just see a hole, right?
Oh,
It would be some like you have to walk around and like you get back to where you started type of like thing. So
but that's interesting too, because like if you're on a torus like this, wait, hold on, I can write right, yeah, right, like this, right? Like for you, like walking around, like how do you know the difference between going like this and then going like that?
yeah, that's true.
How do you know the difference between going in the 1D hole and then going in the 2D hole? Is this a 1D hole, or is this just,
Is it only?
because I know that this like loop around the torus is related to some Betty number, like the one I made in green. I'm pretty sure it's related, because like I did this summer camp that was like about Betty. I did this like summer camp at U of T, and then I think he talked about Betty numbers
Oh, wait,
without
so
using the word Betty numbers. But
so
yeah,
what
I don't
would be
know.
like a 1D hole? So for example, we have a cylinder. Like, would this be a 1D hole? Would that even be a hole at all? Because like it's infinitely long. So
Oh, true. I don't even know. Yeah, I don't know. I have no idea how the Betty numbers work. All right, but that's it then.
yeah.
Yes, differentiable structures. Okay, what did I write down for next time? I'm pretty sure I have like there's another differentiable structures video actually.
Oh, there is. Oh
Yeah.
yeah.